Okay, welcome back everyone. So our next speaker is Mark Hagen, and we'll be talking about hierarchically hyperbolic groups as well. In particular about his new results about simple definition of hierarchically hyperbolic groups via actions on simplicial complexes. So maybe now for the first time, you'll see the full definition or equivalent of that of the of hierarchically hyperbolic groups. Okay, go on, Mark.
Thank you very much. Yeah, so I'll say, let's give this a title. Combinatorial hierarchical hyperbolicity. So everything today that's new is joint with Jason Behrstock, Alexandre Martin, and Alex Sisto. Yeah, so what I'd like to do is I know Federico gave quite an overview of the original definition, and I'm going to remind everyone a little bit about that, and then I'm going to talk about a sort of sufficient condition for a group to be hierarchically hyperbolic. That you can verify by constructing an action on a simplicial complex with some good properties, and I'm going to just sort of talk about the conditions from the point of view of the example of the mapping class group acting on the curve complex, and then maybe if there's time at the end, I'll talk about some applications to algebraic results about mapping class groups of surfaces. So let me just remind you the sort of old school hierarchical hyperbolicity setup. So when I say HHS, I mean hierarchically hyperbolic space. When I say HHG, I mean hierarchically hyperbolic group. So okay, so we've got our I'm going to call it. No, I'm not going to do that. X is a let's say a geodesic metric space. Just you can imagine a graph. And remember that. So I'm going to remind you the sort of data that goes into the definition of an HHS. So the HHS structure. So we have fancy S is going to be a set of Gromov hyperbolic spaces, and when I say Gromov hyperbolic spaces over here, there's an implied constant, right? There's the delta and the delta hyperbolicity, and I want the same delta to work for all of the spaces in my collection. So these are uniformly hyperbolic spaces. And then for each, so we have some relations. So we have a partial order. Called nesting. And it has two important properties. So there has to be a bound on the length of chains. So that's I don't know if Federico used this word, but the complexity of the HHS structure is the bound on the chains in the nesting order, and a unique maximal element. So in the sort of motivating example of the mapping class group, you've fixed a surface, so like an orientable finite type surface of finitely many punctures, and your set S is the set of all the subsurfaces of the surface. So that means like pi1 injective central subsurfaces up to isotopy. And nesting of two subsurfaces is, just if you can isotop one to be a subsurface of the other, then the smaller one is nested in the bigger one. And in that example, X, the metric space is just a Cayley graph of the mapping class group of the surface. Okay, so you have another relation, orthogonality. And orthogonality is just a symmetric, anti-reflexive relation. And we ask that if like one of our hyperbolic spaces U is nested into V, and V is orthogonal to some other hyperbolic space W, then U is also orthogonal to W. So orthogonality gets sort of passed down in the nesting order. And then if two hyperbolic spaces are not related by either of the following relations, then they're transverse. So in the mapping class group case, you say so two subsurfaces are transverse if they overlap. So they can't be isotoped to be disjoint, which would correspond to orthogonality, and they can't be isotoped so that one is a subsurface of the other. And so that's part of the data. The other part of the data that I'll focus on is for all of our hyperbolic spaces, we have a coarsely Lipschitz map. I'll call these pi of U from our main space X, that's sort of the space we're studying, to the hyperbolic space U. And again, I want the coarse Lipschitz constants to be uniform over all of the subsurfaces. And although it's not part of the definition, but it turns out one can always assume that these maps are coarsely surjective. So in the mapping class group case, this is a little bit more difficult to describe if you're thinking of X as being a Cayley graph. Instead, typically, people use a quasi-isometry model of the mapping class group called the marking graph, and they define these maps using something called subsurface projection, which I might discuss a little bit later in the talk when we talk about examples. But so that's sort of the data, and there's a bit that I've left out. In fact, I'll remind you about one more thing from the data. So if U is either properly nested inside of V, so nested but not equal to V, or U is transverse to V, so they're unrelated in the nesting or the orthogonality, we have a distinguished point, which I'll call rho super U sub V inside of V. So I think of this as a constant map from the superscript to the subscript. So these points are sort of, you think of them as projections between the different spaces. And I think I'm not going to talk about too much about the sort of geometric intuition behind this definition, because I think Federico did already a little bit, but I'm going to say what the point is, and then I'm going to switch screens for a second and show you the actual definition in the paper for dramatic effect, so that you can see why we would benefit from having a simpler version. So there are 9 axioms that tie this all together. And the main point is sort of 2 things. The point of the idea, the axioms have been chosen really to prove 2 theorems that you then sort of take as the definition. So is to prove 2 things. So one, I'm going to state one of them precisely, and I'm going to state one of them imprecisely. So I'll do the imprecise one first. So the realization theorem says that if you look at, says that the image of the map from X to the product of all of the hyperbolic spaces, right? So you just take the product of all the, I'm pointing at my screen. You take the product of all of the projections, the Coarse-Lipschitz maps over here, and this image is coarsely characterized by conditions on transverse and nested pairs. So on pairs U and V, such that U is transverse to V, or U is nested in V. So these conditions are motivated by the something called the Behrstock inequality in the mapping class group, and they're also closely related to cat zero cube complexes and constructing those out of sort of set theoretic data, constructions due to Segev. So this is kind of a common, it's at least inspired by both of those things. So I'm going to state the condition for transversality, and there's a similar one for nesting. So the condition for transversality says that, well, if I take a point X in X, and I take U and V transverse hyperbolic spaces, if you look in the product of U and V, so here's V and here's U, inside that product, I'm going to pick a base point, which is rho UV, comma rho VU, and I'm going to look at the union of the 2 copies of U and V that contain that point, and I'm going to take a neighborhood of fixed. There's a certain fixed constant that's independent of all the U's and V's and X's. And the projection of X has to land in that like thickened up cross. So the projection of X has to, either the projection of X to U has to be close to V, to rho VU, or the projection of V to U has to be close to, of X to U has to be close to the projection of V to U. So you just, so a point in the product of hyperbolic spaces that lands over there could be in the image of X, but a point that lands over there cannot. And the realization, so this condition is an axiom, and the realization theorem says that, in fact, up to sort of a bounded error, if I give you a point in the product of all the hyperbolic spaces that satisfies this condition for each transverse pair and a similar condition for each nested pair, then that point in the product is uniformly close to the image of this map. So that's the realization theorem. And then, okay, I'm going to need another page. And the second thing you want to prove that I'll state more precisely, because you can just write it down without a picture, is the distance formula, which I guess you've seen, which says that for all sufficiently large S, there exists a constant A, such that if you give me 2 points X and Y in X, I can estimate the distance between X and Y in X just in terms of the different projection distances. So there's a little wrinkle. So if I look, I sum over everybody in all the hyperbolic spaces, except I restrict myself to the ones where the projections really seriously distinguish the 2 points. So I'm summing over all of the hyperbolic spaces where X and Y project at least S far apart. And then that's going to be, that's going to estimate the distance in X up to the usual quasi-isometry thing. So okay, so it's tempting to think that the distance formula says put the L1 metric on this possibly infinite product of hyperbolic spaces, and then those projections are giving you a quasi-isometric embedding of X into the product. That's not quite true because of this sort of thresholding, right? There are probably infinitely many hyperbolic spaces where the projections differ by like, S over 2 or something. However, there are only finitely, as a consequence of some of the axioms, there are only finitely many where the projections will be bigger than S, and then you sum those. So I didn't tell you the axioms, and I'm not going to, but I will. Let's see if the following thing works. So do I have it? Yeah. So here is the definition. I don't know if you can see that. It's very small, but here is the definition, and there's 9 axioms, and so you can imagine that if I give you a group and maybe it has some properties that make you suspect that it might be a hierarchically hyperbolic group. For example, lots of Artin groups we suspect are hierarchically hyperbolic, but don't know it. It's difficult to verify it because you have to come up with a collection of hyperbolic spaces and then check all these things. And even in the case of the mapping class group, I mean, checking many of these axioms, those are big theorems of Mazur and Minsky from the late 90s. And it's a lot of, you have to understand a lot about the structure of your group usually in order to check that it's hierarchically hyperbolic. On the other hand, the reason you want to prove that it's hierarchically hyperbolic is probably to understand something about the structure of the group. So it's desirable to have a good criterion for checking hierarchical hyperbolicity. So I'm going to first tell you how groups fit in here, or remind you how groups fit in here. And then I'll say a little bit about why you might want to check that something's an HHD, which I think Federico went into a bit also, but I'll just say a few consequences. So finitely generated group G is an HHG. so there's a hierarchically hyperbolic group, if it well, so first of all, if it has an HHS structure. So when I say that, I mean put some word metric on G, and then there's some collection of hyperbolic spaces and projections and all the other stuff that makes the group with that word metric a hierarchically hyperbolic space. And I want G to act on the HHS structure. So that means G is acting on the set of hyperbolic spaces, and G, that action preserves the relations of nesting and orthogonality and transversality. And I want the and I want each element of G to induce an isometry between the hyperbolic spaces. So I'm going to write down some commutative diagrams. So in the original formulation, like everything over here was coarsely commutative, and it was a bit of a mess, but now I'm really drawing commutative diagrams. So this says that if I take a G and G, it acts on the group G by left multiplication. That's an isometry over there. And then when I project down to any hyperbolic space U, I have, when I say G acts on this, I mean there's also an isometry from U to the hyperbolic space I get via the action on the set. And that diagram commutes. This isn't so important for what's later. I'm just telling you what a hierarchically hyperbolic group is. And similarly, if I have two of the hyperbolic spaces, I have these isometries induced by elements of G, and and if I had these constant maps, so if these are transverse or U is nested into V, then I have this special point rho UV inside of V, and this commutes when you think of that choice of point as a constant map. So just if you went through the data in an HHS and just thought of what was the most natural way to say what it means for a group to sort of act on all of that data, then this is the definition that you'd come up with. And so that's right. So that's what it means to be an HHG, and I'll list a few things that indicate why it's desirable to prove that something's an HHG. So, so if G is an HHG, then G is either acylindrically hyperbolic, which has a lot of consequences like SQ universality and things like that, or it's quasi-isometric to a product of two unbounded spaces. So either this is it's a little bit like, there's a few results like this, and I kind of think of them as being like the HHG version of like the rank rigidity conjecture for cat zero groups. G has finite asymptotic dimension. So these two theorems are joint with Behrstock and Sisto from about 5 years ago. If G is not QI quasi-isometric to a product, G has uniform exponential growth, So that's a new result by Carolyn Abbott and Thomas Ng and Davide Spriano from 2019. And so that's kind of a, so uniform exponential growth in this case means that, you know, there's a uniform constant so that for any finite generating set of G, there's two elements of at most that length that generate a free subgroup. So that's like, it's like a strong version of the Tietz alternative, which had previously been proven by Matt Durham, myself, and Alex Sisto, and well, so more, maybe I should have said first, because it's more an even more like basic non-positive curvature type property. G has a quadratic Dane function in other words, you can efficiently solve the word problem in G. So a hyperbolic group, which is like the sort of baby example of G, has a linear Dane function, and when you allow some non-hyperbolicity in there, but in this way that's controlled by the axioms, you get a quadratic Dane function. And this is combining work of Bowditch and then basically Behrstock and Sisto, and I applied a theorem of Bowditch over here to do that. So there's various other consequences. So these are reasons why it might be useful to prove that something's an HHG. But as you can see from the definition, that's not always easy to do. So so there are strong results building new HHGs. So you just heard about one of them. So Berlai and Robio combination theorem. So if you start with a bunch of HHGs and make a graph of groups in a suitable way, you get another HHG. There's a very recent work by Robio and Spriano, another combination theorem, which is not on the archive yet, so I won't do any spoilers, but I think it's very cool. And there's various so those are ways to build new HHGs, and there's also sort of small cancellation quotients. So I guess the prototypical example here is if you took you know, the motivating example of an HHG, the mapping class group of a surface, and you choose a pseudo-Anasov element. So we'll talk about this a little bit more later, but if you know what that is, that's an element. I think of it as just an element that acts as a loxodromic isometry on the curve graph of the surface. So we'll talk about that maybe a bit later. And you take a high power of that element and you quotient by the normal subgroup it generates, then you get another HHG. And some of the applications I'll get to later are sort of in this vein. So what happens if you try to take other sorts of quotients of HHGs? But beyond these results, it's hard to, you know, if I give you a group and say that, tell me it's an HHG, you could try to say that it's built out of old HHGs in one of these ways, or you could try to, you know, look at the short finite list of known examples, which I think you saw earlier. But other than that, it's hard to check. So what I would like to do is now proceed to the main theorem. But first, maybe, I don't know how this works, but does anyone have questions that they want to ask about the original setup before I go to the new setup? I guess you can always use, yeah?
Yeah, I forgot to mention to people that people can just shoot questions anytime they feel like. We don't require people like to raise hand or anything. We prefer lively setting. But
Yes.
So if anybody has a question, just feel free to shoot at Mark. But
Definitely.
So far there are no questions.
Yep, this is okay. So I'm gonna, yeah. So yes, please stop me if you wanna, if you have something to add. So okay. So now I'm gonna talk about the combinatorial criterion. So so what it does, so it's not an equivalent characterization of being an HHS. The converse of this theorem is not true, although we're working on a sort of partial converse right now. But so I'm going to state it does get the 9 axioms down to 4. And so I'm going to state the theorem, and then I'm going to just tell you why the different conditions are there using the example of the curve graph of a surface. So first, I'm going to make a definition, which is basically just terminology. So fix a group H and a simplicial complex. So now all of this nasty coarse geometry is gone, and we're just going to do simplicial complexes. So a simplicial complex Y with H acting on Y by simplicial automorphisms. So we say Y is a hyperbolic H space if Y becomes hyperbolic after adding finitely many H orbits of edges. So so for example, you could start out, so when I say Y becomes hyperbolic, that implies a metric on Y. You can just imagine the graph metric on the 0 skeleton. So just, the standard combinatorial thing. And then after adding finitely many more edges, you get a new graph metric where, in principle, lots of distances have gotten a lot smaller because you've put in new edges. If Y is connected, this isn't saying very much other than Y was already hyperbolic. But I'm not asking that Y is connected. So the sort of simplest example you can imagine over here is maybe I have a hyperbolic group H, and my simplicial complex is just the discrete set of vertices with the vertex for each group element. So that has the metric there is pretty boring. Any 2 points are at infinite distance, right? But then when I add finitely many orbits of edges, I have just made a Cayley graph of a hyperbolic group, and now it's a hyperbolic space. So that's the kind of thing you should have in mind. So this is just shorthand, because we're gonna in the theorem we're gonna be allowing ourselves to add edges in order to make things hyperbolic. So let's state the theorem. So this is with the guys mentioned at the beginning. So we're going to start out with a flag complex. that's a simplicial complex where anytime you see a complete graph in the one skeleton, its vertices actually span a simplex. And I'm going to have G be a group acting on X co-compactly with finite stabilizers of maximal simplices. So the conclusion of this theorem is going to be that G is a hierarchically hyperbolic group, which means that I'm going to need to construct a hierarchically hyperbolic space on which G is acting properly and co-boundedly. Now X is not going to be that space because, for example, I mean, non-maximal simplices in X might have very large stabilizers, and there's no hope of a proper action. Instead, if I looked at maximal simplices and thought of them as vertices, then that's going to be the sort of Cayley graph of G, or of course Cayley graph of G that I'm building over here. So I'm asking for finite stabilizers of maximal simplices. X is going to be a database that records all of the data of an HHS structure. And you need to say 4 things to do that. And the key objects are going to be links of simplices in X. So when I say the link of a simplex, I mean just the subcomplex consisting of spanned by the vertices that are joined to every vertex in the simplex I'm looking at. So for all simplices delta, I'm going to ask that the link of delta is a hyperbolic H space where H is the stabilizer of the link. I haven't said stabilizer of delta. I really mean the stabilizer of the link of delta. So the idea being you could have a lot of different simplices with the same link as delta, and I'm allowing the group I'm looking at acting on the link is allowed to permute the different simplices that have that link. I'm just asking for the link to be stabilized. And so I'm saying if I added finitely many orbits of edges to the link, it would become a hyperbolic space. And the other conditions, so the second condition, so this you should think of as one of the main conditions over here. The second condition is also going to be one of the main conditions, and the other 2 conditions are probably relaxable. So this says that if I look at the link of delta, that includes into a certain subcomplex of X, which is X so I'll write it and then I'll say it. So inside of X, if I look at the link of a simplex delta, in the graph metric on X, that link has small diameter, right? It has diameter 2 because for any 2 vertices in the link, they're both joined to all the vertices in delta, so I can just hop to delta and then hop over. So I can sort of think of delta as coning off a certain subspace, right? Delta's sitting there killing the geometry of its link. Now, there might be other simplices that do that. So when I write sigma twiddle delta, what I mean is sigma is some other simplex that has the exact same link as delta. So this is asking that like the link has this interesting geometry, but it's all being killed by being a link. But if I remove all the simplices with that link, then in what's left, the link is quasi-isometrically embedded all of a sudden. So and quasi-isometrically embedded in the metric that you get when you add the edges to the link of delta. So these are the two sort of key things, and I'll explain. I'll show in the curve. These are again modeled on the situation in the curve graph of the surface, and I'll explain why these things hold over there. So these are kind of the main things, and then I think any theorem of this form will have these two conditions in it, and then there are two other conditions that I think are more flexible. So for all simplices sigma and delta, there exist other simplices pi and pi prime such that the link of sigma intersect the link of delta. This is weird, but it's just what the curve graph tells you. So you want to say that the intersection of two links is a link again, but that's not quite true. So this star means a join of two simplices. So this is saying that that links decompose as the join of a link and a simplex. Let me check how I'm doing on time. Okay. So I'm gonna. This is actually natural, and I'll show you in the curve graph in a second. What this is for, among other things, this is for verifying that the nesting condition in the HHS structure we're going to build about this, the condition on bounded chains holds. It's used in a couple other places too, but that's an example of where it's used. And then the final condition, which is very relaxable, depending on the context, says that if delta is not, so delta is a simplex, is not a codimension one face of a maximal simplex. So if it's a smaller simplex, then it has a connected link. Connected before you add the extra edges to make it hyperbolic. Yeah, so I'll quickly, then I'll say the conclusion. Then G is an HHG. So if I make this a little bit smaller, then I can fit the whole theorem. Okay. So a few things over here. So the empty set inside of X counts as a simplex. So the first condition says that, so the fourth condition says that X itself is connected because X is the link of the empty set. And the first condition then says that X is this hyperbolic simplicial complex that you're acting on. So this is really a theorem that says if G is a group acting on a hyperbolic simplicial complex whose links have the right properties, then it's an HHG. Now, the way you extract an HHG structure out of this, in the interest of time, I'm not going to say too much about it because I'd rather draw pictures of surfaces. But the way the set of hyperbolic spaces that you're going to use as your HHS structure are just the links of, are the hyperbolic, are the sort of links of the simplices after adding these extra edges to make them hyperbolic. So that's your family of hyperbolic spaces. And it's condition 2 that's going to allow you to define the projections. So basically, most of, or quite a bit of the work in proving this theorem is showing that this space is hyperbolic. So once you delete the simplicity, like the simplex, and look at what's left with the extra edges, you have something hyperbolic. Now the link is quasi-isometrically embedded by hypothesis, and quasi-isometrically embedded subspaces of hyperbolic spaces admit coarsely Lipschitz retractions, and that's the thing that you use to define the pi maps in the HHS data. Nesting is just containment of links. Orthogonality, I won't write it down. So it's, well, I will write it down just over here. Delta orthogonal to sigma means that the link of delta sits inside the link of sigma. And so those are your relations. And then, yeah, from there, we checked the 9 axioms. And so now, if you're lucky enough to be able to construct such a complex, then you can build HHG structures. So maybe before I talk, I claimed that this is useful in practice. So before I talk about the curve graph a little bit, I'll state but not talk about further. So here's a theorem that I won't state carefully. This is for rhetorical purposes. So this is with Martin and Sisto. Many Artin groups are HHG. So if you know about Artin groups, what you need, so Artin groups are defined by a graph, a finite graph, and there's an integer labeling each edge, and from that you can read off a presentation, and that gives you an Artin group. And we've proved this in the case where all the labels on the edges are at least 4. And so they sometimes call these Artin groups of extra large type. And I'm just saying this here, it's parenthetical. The way this is proved is we've built an appropriate X and checked that the above theorem holds for it. So this actually has utility for studying groups from nature. But I just want to do an example, and then maybe talk about the mapping class group. So so there's a surface. My X is going to be the curve graph. So the curve graph has a vertex for each isotopy class of simple closed curves on S, and edges in the curve graph correspond to disjointness. And I want a simplicial complex, not a graph. So you can fill in you can take the flag complex on the curve graph to get a simplicial complex. And let's play with some links. So I just want to show you why links are hyperbolic and things like that. So there's S, and a simplex is a collection of disjoint simple closed curves. So there's one. So let's call it, so in the curve graph, I have a vertex for each of these curves, and they're all disjoint. So that's a simplex. And now what's the deal with the link? Well, there's a curve that's disjoint from all of those red ones. So that curve's in the link. That curve's in the link. And then all of the simple closed curves inside this once punctured torus that I've cut off over here are also in the link. So what you see is there's the surface that's everything, the subsurface that's everything to the right of these two red curves, this twice punctured torus. The things that are disjoint from all the red things are exactly the curves on this twice punctured torus. So the link of delta is the curve graph of that twice punctured torus, and curve graphs are hyperbolic by a theorem of Mazur and Minsky. So in fact, for all of the subsurfaces of this surface, with some notable exceptions, the curve graph of that subsurface arises as the link of a simplex. So that's like the main way that you get hyperbolic links and verify the first condition in the theorem. The second thing that can happen, though, not every link is a curve graph of a subsurface. So if I make a slightly different simplex, this simplex, triangle, everything in there is disjoint from this curve, which I'll call gamma. So it's a zero simplex of the curve graph. And everything in this once punctured torus, like that curve and that curve, those are in the link. So, and then nothing else is, right? Any other curve that doesn't live in here or is not that one has to intersect one of the red ones. So what you get is that the link of delta is the curve graph of this once punctured torus together with gamma. So gamma does not count as a curve in the once punctured torus. The curve graph only has non-boundary curves as vertices. But what I do see is that there's a join over here, because this gamma is disjoint from every curve on the once punctured torus. And so I get a join structure on the link. So this is hyperbolic because it's bounded. But it also explains why we have this weird condition, condition 3. So we've just seen an example where the link of an individual simplex decomposes as the join of a curve graph, which is you can realize that as the link of a simplex, as in the first example, joins with another simplex. So this is the link of a slightly different simplex, and that's a simplex there. So it has this join structure. So since individual links of simplices can have this join structure, like that's the best you can say about intersections of links. So that's why we have that condition. Okay, about 5 minutes. Okay, what else? So you've seen that links, you've seen, at least in this example, that links are hyperbolic. Sometimes they're bounded, sometimes they're curve graphs, and it turns out that that's the only thing that can happen. Most of the time they are connected, but I want to show you the situation where they can be disconnected. So the fourth condition said that you are allowed to have disconnected links, but it's only for simplices that are like almost maximal. Codimension 1 faces of maximal things. So a maximal simplex in the curve graph is a Pantz decomposition. It's a maximal set of disjoint simple closed curves. And I'm going to look at a simplex which is almost a Pantz decomposition, except it's missing a curve. So there's my delta is this. Wait, I need another one. No, I don't need another one. What have I done? There we go. Oh yeah, that's the one that was missing. So I have this 5 simplex, and the link of delta is I lied a little bit over here, because what you're thinking is that the link of delta is the curve graph of, I said that the link of delta was the curve graph of a once punctured torus over here, and you think that's what it is over here too, but really it's just the vertex set of the curve graph of a once punctured torus, right? All the curves that are disjoint from all the red stuff, they're all curves on this once punctured torus. You can't have 2 disjoint curves on a once punctured torus. So the definition of the once punctured torus is one of finitely many surfaces, where the definition of a curve graph is a little bit different. It's still hyperbolic, but it's totally disconnected, right? I can't draw 2 disjoint curves on here. So the link is disconnected. And now it turns out that this is the only way that the link can be disconnected, because in general the link is like either a join, or it's the curve graph of some or it's the curve graph of some subsurface, and it's only when that subsurface has complexity 1, like it can only contain 1 simple closed curve without having 2 intersect. It's only in that case that the curve graph as defined here is disconnected. And so that what that says is that if my red curves in my simplex cut out a surface with bigger complexity more than 1, then the link will be connected. Otherwise, in this codimension 1 case, the link will be disconnected. So that's the 4th condition. You can't use our theorem, though, to prove that the mapping class group is an HHG. Here's why. So I'm going to tell you why, and then I'm going to tell you what you can prove about the mapping class group, and then I'm going to stop. Our theorem, so the mapping class group acts on the curve graph, and a fun exercise in the classification of surfaces is that it acts co-compactly on the curve graph. There's finitely many orbits of families of disjoint simple closed curves. But if I take a maximal family, right, so if I actually take a Pantz decomposition, so delta is this 6 simplex, the stabilizer of delta, which is contained in the, the stabilizer of delta is not finite, because for each of these curves, there's a homomorphism of the surface, right? There's the Dane twist around that curve, and that Dane twist acts as the identity outside of a neighborhood of that curve, and so it stabilizes, all the other curves, and those Dane twists all commute with each other. So we have a giant free abelian group inside the stabilizer of that simplex. So you can't possibly have a proper action over here. So, so you can't possibly have an action with finite stabilizers of maximal simplices. So the mapping class group action on X does not have finite stabilizers of maximal simplices. So the theorem doesn't, so the setup for the theorem applies to the curve graph. Like all the combinatorial stuff holds in the curve graph, but the action's not good enough. You don't, although the mapping class group is an HHG, you can't see it this way. And now you're wondering why we modeled our theorem on the curve graph when it doesn't apply in that case. And so yes.
I just want to check, weren't the two loops on the right-hand side of the surface isotopic?
Oh, sorry, I drew too many curves. Thank you. I got excited. Yes, because there should only be 6 and I drew 7. Thank you. Yeah, those two Dane twists I drew were the same. Yeah, so what I'll finish with is I'll just state the theorem that explains why we modeled this theorem on the curve graph, because we were after something to do with the mapping class group. So remember before I said that when you quotient the mapping class group by high powers of pseudo-Anassovs, you get another HHG. And we're interested in the question of what if you quotient by high powers of Dane twists instead? And this is something that had been studied by Francois Damani, who gave he took the mapping class group and he looked at the subgroup normally generated by powers of all the Dane twists, and he gave a really explicit description of that subgroup. And so we wanted to see that the quotient of the mapping class group by that subgroup is a hierarchically hyperbolic group again. And so that's what sort of motivated this approach. So so the theorem says that if well, so there exists a K. So there's a certain power such that well, n greater than 0, the following holds. Let n be the subgroup normally generated by so this is your favorite power of Dane twists that's divisible by K. So T. So you have to look at all the Dane twists inside the mapping class group. So that's a subgroup of then that quotient is a hierarchically hyperbolic group. So this is, so there's a new example of a hierarchically hyperbolic group that could not have been produced by existing methods, and this uses the action of the mapping class group on the curve graph, and sort of you then quotient the curve graph by the action of this subgroup, and that's another simplicial complex where this quotient acts, and you verify the hypotheses of the previous theorem for that simplicial complex. And the corollary that we were really after is weird, so I'm going to finish with it. So if every hyperbolic group is residually finite, then the mapping class group has many, it's not quite a corollary, it's a thing you prove in the same sort of way. It has many hyperbolic quotients. So there's an open question that I think generally people believe the answer is yes. Like, does the mapping class group admit, infinite hyperbolic quotients? On the other hand, nobody thinks that every hyperbolic group is residually finite. So the idea, the reason why I like this corollary is, on one hand, it could turn out that someone comes up to me tomorrow and says, the mapping class group of a genus 17 surface doesn't have any hyperbolic quotients for some other reason. Therefore, there's a non-residually finite hyperbolic group. On the other hand, what I think is more likely is that someone will be able to look at the proof of this and look at the different hyperbolic groups that are encountered during the proof that we need to find deep finite index subgroups of to make the proof work, and those are fairly explicit hyperbolic groups. You could write down presentations of them, and they're interesting candidates, I think, for trying to see if they're residually finite. So there's sort of a new class of hyperbolic groups for which I hope someone goes and proves residual finiteness. Yeah, I'll stop there. Sorry for going a bit over.
Thank you, Mark. It was really nice. Are there any questions for Mark?
Yes. Hi, Mark.
Hi.
So do you have maybe an example of an X when you're looking at a product of cat zero cube complexes? So maybe just for Z square.
Right. So okay. So for that's a good question. So for Z squared, let's do it for Z squared. So you take so the idea, so the X for Z squared is going to be bounded, and it's going to look like this. So you this construction works for rags, and it's closely related to the proof for the other Artin groups that I mentioned. So if you know, so for right-angled Artin groups, Sam Kim and Thomas Caberta defined this thing called the extension graph, and it has a vertex for each of the conjugates of the standard generators, and it has an edge joining two of those vertices when the corresponding conjugates commute. So for Z squared, which is a right-angled Artin group, it's not very interesting, right? There's A and there's B. That's the extension graph, and so that's not good as an X. So the action on here is by conjugation, if you think of it that way. Yeah. So so that's not good because it doesn't act, for instance, with finite stabilizers on this maximal simplex. So what you can do in general is you can blow up the extension graph. So for each vertex in the extension graph, you put a copy of the corresponding cyclic subgroup sitting below it. So you blow up the vertex to the cyclic subgroup, and then whenever you have an edge in the extension graph, you blow it up to a join of those two. I just, well, right, like when I blew up that edge to a little bipartite graph like that, right? I made a little squid, and then each edge in the extension graph corresponds to a join of squids. So I have simplices like this, right? If I have these two vertices, they span a, like for any vertex over here, those three span a simplex. I have simplices like that. So I have lots of, in fact, I have also some three simplices that are joins of an edge here with an edge here. So the stabilizers of those three simplices are trivial, and this turns out to be the right x to use for z squared, and in general that's an x you can use for right-angled Artin groups. And in fact, I think it's this construction of blow-ups that makes the theorem useful. So if you were careful, remember I said that you can't recover the HHG structure on the mapping class group from that theorem because the curve graph isn't quite good enough to be able to see those Dane twists. But I think you can blow up the curve graph in this way by sort of replacing each vertex with something that's coarsely a copy of Z, and do this sort of blow up and join construction and verify it there. So there's not like a well-articulated theory of this blow up and join construction yet, but it seems to work for different examples, and I think it's the thing that should be used in tandem with the theorem. Does that answer your question?
Yes, but does this work for a product of cat0 cube complexes if it's maybe not a RAG?
If it's not a RAG, so not every cat0 cube complex is a hierarchically hyperbolic space. So if the what I suspect you'd have to do is take a cat0 cube complex which doesn't have, have you heard of the different pathologies in the cat0 cube complex that can make it not be an HHS?
Is it pathologies for not being special?
So that's a good, so it's a little bit more, there are, yeah, let's say you have a special, let's say, so special cube complexes are all, their universal cover of a compact special cube complex is an HHS. So if you took two of those and took the product and you wanted to see the HHS structure using this theorem, I suspect what you could do is take the crossing graph. Let's say you wanted to do it just for one of the factors. I think you could take the graph which records the crossing of the hyperplanes, and you'd have to blow up the vertices in the appropriate way, and then do this construction. I haven't thought through exactly how that works, but I think you can see it that way. Yeah, but I don't know. I think this has to do with, I mean, originally, many years ago, we were thinking about links inside the crossing graph of cube complexes and trying to do stuff that way. And we, and that's what led to the definition of an HHS. So this is sort of going back to the original thing, but I don't totally understand links in the crossing graph of a cube complex. So that would be a good thing to think about.
That's very interesting. Thanks.
Yeah. Yep.
Are there any other questions for Mark? Well, I have one just short question.
Yep.
Oh yeah, but there was somebody else also wanted to ask, so I'll ask my short question. So Mark, you said that from a work with Alexandre Martin, you showed that many Artin groups are HHGs. So I'm just curious, because following some of the stuff you mentioned, what problem in HHGs is in NP. So does your proof actually showed that word problem in some Artin groups that is solvable, that was not known before, or even improve the complexity by putting it down to NP?
I don't know what was known before about the word problem for extra large type Artin groups. I suspect that there were already efficient solutions to the word problem for them, but I'm not sure. So the solution of the word problem for HHGs goes via the fact that they have quadratic Dane function, and that might have already been known for extra large type Artin groups.
Oh, okay, thank you.
Yep.
Hi, Mark. I have another question.
Yeah.
When you have a hierarchically hyperbolic group, then you can put a hierarchical structure in the Cayley graph of that groups, in the sense of the first part of your talk.
Yep. Yeah, that's right.
That's right. Okay.
Yep. Yeah. So that's
so that means that the action is proper, right? Yeah.
Yes. So right. So the way I formulated the definition was the Cayley graph is itself like the X in the first definition I was talking about. It is a hierarchically hyperbolic space, and so the action, right? So the action on it, so in particular, you have a proper co-compact action on a hierarchically hyperbolic space.
Okay, thank you very much.
Mm-hmm.
So if we don't have any other questions for Mark, let's thank him one more time. So feel free to hit your reaction buttons.
Thank you for having me, Michael. This was fun.
Yeah, thanks for, well, coming, for joining in.